Hello, everyone. Thanks for listening to my talk. Today, I'm talking about fixing bias in reconstruction-based anomaly detection with Lipschitz discriminators. This is a project with me, Guy Wolf, and Smita Krishnaswamy. Guys at Mila and Smita and I are at Yale. So just to go over the high-level problem, anomaly detection is a large field. However, we're looking at a specific problem where given samples from the nominal distribution, we produce an anomaly scoring function that is high on anomalous points and low on nominal points. This also goes by a few other names as outlier detection or anomaly detection, depending on what field you come from. So we're specifically focused on deep anomaly detection, and this is normally done on image classification data sets. So for instance, here's a data set, and we split up the data into training data and test data. We take one class as the nominal class for the training data, and then on the test data, we take that class versus all other classes. And so we only get the nominal data in training, and we're supposed to classify this kind of data versus all other classes. The typical way this is done is using a reconstruction-based anomaly detection system. So this involves an autoencoder with an encoder and a decoder and a middle layer that is restrictive. The training is done with a mean squared error loss, and the scoring is done also with a mean squared error loss. So how this works is we train only on the training data. This is only on nominal points, and so the idea is that mean squared error will be low on these points or points of this type and high on everything else. So scoring by this function, we should get a mean squared error that is low on nominal points and high on anomalous points. And so this leads to a description of anomalies that are implicitly defined as inputs that are difficult to reconstruct based on this model. And this presents some problems that we'll discuss a little bit later. Starting from the other direction, let's describe some desirable properties from an anomaly scoring function. First, we might want similar inputs to have similar scores. We might want to be robust to a small number of anomalous samples in the training data. And we want very distinct points from the training set to be classified as anomalous. And so here's our toy example, an input data that's a circle, and red is more normal scored, and blue is more anomalous scored. B is the autoencoder, and C is our model. So you can see here that the autoencoder, depending on the model, has some of these undesirable properties, whereas LID, our Lipschitz anomaly detector, has all three properties. And so we base our discriminator on a optimal transport view. So we're looking for the one Lipschitz scoring function up to a constant that the Kantorovich-Rubenstein witness function between the nominal and the unknown anomalous distribution. So take the picture on the right, for instance. Blue is the nominal distribution. Orange is the corrupted distribution, and the optimal F between the two, the scoring function, would be the green. Getting into this, just a little bit about optimal transport and the Rubenstein duality. So the one Wasserstein distance between two distributions, P and Q, is defined as the infimum on the joint distribution that minimizes the total distance, total expected distance. And so this can be thought of as P as piles of dirt and Q as holes in the ground, where we're trying to map which piles of dirt go into which holes. And so another way of expressing this is with the duality. And so if we have a witness function F that is defined over the entire space, F is a function from the real space to the real numbers, and we're looking for the function that is both Lipschitz and maximizes its value on the distribution P and minimizes its total value on the distribution Q. F is known as the witness function. It witnesses sort of the differences between P and Q. So it should be high in the places where P is higher than Q and low on the places where Q is higher than P. This is exactly how our Lipschitz anomaly discriminator works. We have a training distribution Pn, a corrupted distribution Pa hat, which is supposed to mimic the real anomaly distribution Pa as closely as possible. And then we calculate the optimal discriminator using F as parameterized by a neural network that maximizes its value on the training distribution Pn and the correct distribution PA hat. And so obviously there's this question of how to train a neural network that is Lipschitz function and to optimize over the class of Lipschitz functions. There's been a number of works, especially in the Wasserstein GAN arena, how to make a Lipschitz discriminator, which also solves for the Wasserstein distance. So the first work was the original Wasserstein GAN paper, where they just simply clip the weights of each matrix from -C to +C, some small constant that they predefined. The second way was to penalize the norm of the gradient everywhere to be close as possible to 1. And the third was to use spectral normalization to divide by the spectral norm, and so that the Lipschitz constant was always 1. We found that the second one was most helpful and worked the best for our case, so we're going to use that from now on. So first thing I'll describe is theoretically how our Lipschitz anomaly discriminator is affected by corruption of the training set. And what do we mean by this? So adding anomalies to the training set does not affect the scores very much is the general idea. So let f star be the optimal scoring function and f star star be the one under the corrupted training set where we add gamma percentage of anomalies to it. Then you can see on the right the optimal scoring function for one example where the anomalous distribution is at 1 and the normal distribution is at -1. And we can bound the difference when we add this training noise. And so, just to get an idea right here, if we added some noise to some anomalous points to the nominal distribution in the training set, then we still get the same optimal discriminator. And we can bound this for all cases based on a number of other factors that you should look at the paper to fully flesh out. And so the second thing we want to say is how far away from the training data, then we should score everything as anomalous. And this is not the case in a normal reconstruction-based autoencoder. But we prove that outside of some large radius, then every point is scored as anomalous. And this arises due to the fact on the right, you can sort of see if we have an anomalous distribution that has larger support than the nominal distribution, then the optimal f star will keep going down outside of the sort of range of the nominal distribution. And so just revisiting these original properties, we're looking for similar inputs that have similar scores. And this is using a Lipschitz property enforced by a gradient penalty so that the function is 1 Lipschitz, and we're looking for only scoring functions that are smooth. And then to be robust to a small number of anomalous samples in the training data, we showed that adding a few does not change the optimal F value very much. And finally, for very distant points from the training data, we classify them as anomalous. This is assured in ours and not in autoencoders. So empirically, we look at training set corruption. And the reason we look at this is it's very unrealistic to assume that we can get rid of all of the anomalous points before training, right? If we have a very large training sets, then millions of images maybe, we might not be able to clean all of the anomalies out. There may be 10 or 100 left in a million-size data set. And so the mean squared error training means that you sort of optimize for the worst score, right? So since it's squared, then the worst score is the largest effect on the gradient. And so this means that if you add a little bit of anomalies to the training set, then these will also be pushed down and have a low score. And consequently, if the anomalies all have very similar inputs, then you may push down the score of all anomalies, even if they weren't in the training set. So this is the intuition by why autoencoders might not work very well when you contaminate the training set. So to set this up, we use the same data. However, we add corrupted, and corrupted we mean by adding other classes to the training data. So these are treated as nominal in the training process. However, they are actually anomalous. So when we do the test data, we will have cars that were in the training data, but now should be classified as anomalous, however, a very small percentage of them. And so the way we analyze this is over a bunch of different models. We look at some percentage of the training set being corrupted, and we look at the area under the receiver operating characteristic over each, and the mean over each digit. So we compare against a bunch of different methods. Higher scores are better here, and some of these are reconstruction-based. And so the reconstruction-based perform very well. For instance, the convolutional autoencoder or the denoising convolutional autoencoder do very well with zero training set corruption. In fact, outperform our model. And this last line is our model plus a convolutional autoencoder, so an ensemble between the two, just to test whether the benefits can be combined. And so, but you can see the convolutional autoencoder, the performance decreases pretty sharply as we add training set corruption. So at 10%, it performs quite poorly relative to others. And so another thing we did was take the all black image for MNIST. So this is an image that is not in any digit, but it is somehow very far away, right? So all of the training digits have a lot of white pixels, black image is fairly far away. And we rank its percentage anomaly when trained over the full training set. So for instance, here we train on all of the MNIST ones and score the black image versus the score of all the ones. And 1 means that it is scored more anomalous than all of the training data. 0 means it's scored less anomalous than all the training data. What this is really trying to show is that when you do reconstruction-based scoring, then you have this problem where some points are easier to reconstruct than others. In that a all black image is actually quite easy for a convolutional autoencoder to reconstruct, pretty much no matter the architecture or the training data. And so this shows, right, even though we have a large training set, all of them score the black image very, very low. And so they all think the black image is part of the training set, where our model does not. We tested this on a healthcare data set. So this is the VACS, the Veteran Aging Cohort Study. And this has a bunch of panels. One of them is creatinine, which measures liver function. So we took high creatinine as anomalous, and this represents abnormal liver function. And so we did exactly the same thing as we've been doing on the image data sets, testing against all models. And we found, since these anomalies are all very close together in that patients with high creatinine have a lot of the same signal, it means that if you add even a very, very small amount of corruption to this kind of data, then you drastically deteriorate the scores very quickly for most deep learning methods. And whereas ours, it stays high no matter how much training set corruption you add because of the robustness properties. Finally, we also tested on CFAR10. We have over all the classes perform better on some and perform worse on others. And we explore a little bit why. So for instance, planes and cars, we performed quite well, whereas birds and dogs, we perform not as well. But overall, we perform fairly evenly with all the other methods. And then when adding ours to a standard convolutional autoencoder, then we can improve over the other versions. And so the reason that the reconstruction-based methods do well on some and not well on others compared to ours is that reconstruction methods really like images that look like the mean. So here are some images of the most nominal cars in the test set for our method and for a denoising convolutional autoencoder. And C shows the mean image of each class. So you can see here that even though this is trained on all cars, it really prefers things that look like the mean car, even though they are not cars. And so this really shows why maybe combining the two, or the problems with just using reconstruction is that it loves the mean image, whereas our model really scores things that are like cars to be similar. So in conclusion, we have our standard autoencoder, and it implicitly defines anomalies as hard for the model to reconstruct, leading to a few different issues. And we fix these issues with additional of a neural network based on optimal transport theory, which we call DLAD. Combining LAD with existing models gives state-of-the-art results on standard MNIST and CFAR10 benchmarks. Thank you very much. Please feel free to email me, and the code is available on our GitHub. Thank you.